Yeah, good evening all. So let's start today's session. Uh, so the count is quite less today. Anyways, so I have shared a link in the chat for the Replit session, right? You all can go over there and do the coding, but I have yet not published the programs. Before that, I have some few questions to ask, and then we will continue the live coding. I am audible, right? You all can hear me?
Yeah, yes, yes.
Yes, sir.
Okay, okay.
Yeah,
Fine.
sir.
Okay, fine. So before moving into the live coding, there are two things that I want to ask and discuss. The first one is regarding the asymptotic time complexity. So we have seen more than one discourse post asking about confusion on time complexity function comparison, that which function is, I mean, is has a higher growth rate and which has a lower growth rate, right? So there are few questions on that. So I would like those of you who are present now, how many of you are totally confident about this topic, comparing two function on the basis of their growth rate for asymptotic complexity? Please be honest about it. Huh? Anyway, I will discuss briefly for a few minutes and then we will move. So please raise your hands who are totally confident about it. Okay, I see no hands raised. So I mean, can someone then address it? Can someone tell that you all feel problem in that, or anything, any specific problem you want to put forward? You can unmute and tell.
Sir, you said totally confident. That's why I didn't raise my hand, but I'm more or less confident. I guess it's the same for others as well.
Achha. Okay, so I would just briefly discuss one point about it, although it's a little bit advanced one, and we have not discussed that in detail in the lecture. But still, since this doubt is coming multiple times, I want to discuss it. My screen is visible, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. So see, this is one way to actually formally check which function has a steeper growth rate. Huh? Other than seeing, so what you all generally, most of you would have done till now is simply put a value in the function and check. Some of the functions are quite easily by only by seeing the functions you can understand that this is more steeper than the other. That is, the growth rate of a particular function is greater than the other. But in scenarios where you cannot identify, generally you put some value and check. I mean, for the same value, what is the result of both the functions? If someone else prefer any other technique, can you just tell by unmuting yourself? Okay, so I'm kind of assuming that is what everyone does. So see, there is another way. I mean, I hope all of you are quite comfortable with differentiation and limits, right? You all have done that in the math courses, correct?
Yes, sir.
Okay. So you all have done about the L'Hopital's rule, or many say it as the L Hospital's rule, but yeah, generally it's pronounced L'Hopital's rule.
Yes, sir.
Okay. So see, what you all can do is, generally, what is growth rate? What is asymptotic complexity? We actually consider the complexity or the growth rate of a function when you have very large input, right? That is the essence of asymptotic complexity. That you consider functions when they are growing at a the growth rate when the input size is very large. This input size being very large is very important, right? That is why we considered this in the definition. We said that for every n which is greater than n naught, right? Before n naught, it can be some. I mean, a particular function may show some other characteristics, but after a certain threshold, which is my n naught in this case, right? That is for sufficiently large input. This formal line actually, I mean, translates into the English statement for sufficiently large input. That's it. Okay. So this is the mathematical way of writing that. You have to check the growth rate of that function for sufficiently large input. So my sufficiently large input of n is very important. And that's why what we will do is we would do limit n tends to infinity. Fine. For huge numbers. Now in whatever function, whatever the two growth function that you want to compare. So let's say log of n square. Okay. And let's say root n. These are the two functions that I want to compare. Which one is larger? Fine. All you have to do is, obviously you can see both of them are infinity by infinity, that kind of form. So what you have to do is you have to apply the L'Hopital's rule and you have to differentiate. Fine. So let's do the differentiation. So this would be log of n square means 1 by n square according to the chain rule of differentiation. And this would be 2n divided by, so this would be half, that means, yeah, correct. So this is the differentiation that I get. Again, limit n tends to infinity, same thing. Fine. But now we can cancel some terms. So here 1n cancels. And obviously this is root n. So again, this would become root n again. This 2 would go up. So ultimately I get something like 4 by root n. I hope that should be correct. Yeah. 4 by root n. So again, limit n tends to infinity. So which you get 4 by infinity, that is 0. Fine. Now see, this is the fact. When I get 0, either you will get 0 in the answer or you will get infinity in the answer. Right? If I would have taken root n by log n square, you can take any one of them, doesn't matter. Only thing you should conclude it properly. Then I would get at the end infinity. Fine. So if you get infinity in the answer, you would understand that obviously the top function is larger. And if you get 0 in the function result, then that means the denominator was larger, whichever function you took in the denominator. Correct. So here root n is larger. So simply by using this method, in most of the cases, there are actually corner cases where this would not work and we use some other techniques. But even this is not there in your course. But this is one good way to actually, sometimes for complex functions, you can actually do this and check. Any doubt in this question? Any doubt in this discussion?
Sir, what are the cases in which this will fail? Maybe due to continuity or some other thing?
Exactly. If there are let's say the asymptotic, those things would not turn up in this course for sure. Mainly if you do some academic research work, then those kind of things comes up. So there can be complexities points where it can be discontinuous. So you cannot differentiate at that part, or maybe it is not differentiable. So let's say the modulus function, right? I mean, you all have learned modulus function, correct?
Yes, sir.
Yeah, so if you check the graph of modulus function, most of the time it would be something like this. Right? Sorry, this should be the tip. Right.
So, sir, can non-differentiable, non-continuous complexities also exist?
Generally not. Theoretically, not. Non-continuous would never exist, but non-differentiable may exist. I mean, you can. It's a growth function, right? In terms of algorithm, it may does not come directly, but it's a growth function. So if you actually check growth function, or many a times what we do now, let me tell you. So you have to compare two growth function, which is something like this: n into n minus 1 into n minus 2 dot 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 1, which is ultimately n factorial, right? Which is equal to n factorial. Now I am telling you order of n factorial. Now we have not intuitively done any n factorial asymptotic complexity kind of thing, right? We have done n square, n cube, 2 to the power n, any that kind of figure. So many a times what we do is, in order to find the upper limit, that is the worst case, we actually take some function which is greater than the function. So n factorial is n into n minus 1 into n minus 2, this, right? So what I would do is I would consider, since I am considering worst case, since I am considering the worst case, which is the upper limit, I can take a function greater than this value. I cannot take lesser, but certainly if I am considering order, I can take a greater function. So what I would do is I would write n dot 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 dot.
N to the power n.
Correct. So this would be n to the power n, and I write that n factorial can be written as order of n to the power n. There is actually a much better proof of this and proper form of this conversion. I mean, this is just for the intuitive idea, but n factorial is actually representable into the form of an expression where the highest power is n to the power n, and that approximation is called Stirling approximation. So if you are interested in that, some of you can check that. It's called Stirling approximation. Okay. But basically the highest term is n to the power n in that approximation. So many a times we do this kind of approximation for proving something, right? In that kind of scenario, when we actually assume a function greater than some real function which came up because of the algorithm, in that kind of scenario, you can come up with arbitrary growth rate function, some typical different mathematically complex kind of growth rate function. So there it can be something which may be not differentiable, right? So things turn up, something like that may turn up, but in real life, generally those things doesn't turn up. Mainly in mathematical proof of complex algorithm or approximation algorithm, something may turn up. Fine. So those things are there. Okay. Anyway, these things doesn't matter. Anyway, this was not required, but I just wanted to discuss this because this is a good way to actually check, a more formal way to check complexities. Yeah. Any more doubt?
Also, sir, this Stirling approximation would hold in the limit and tends to infinity only, right? So that's why we can use it here.
Yeah, that's why we are approximating. If you actually go by Stirling approximation's actual formula, that may also hold. I'm not sure about that, but I think that should even hold because there is a greater derivation for that approximation. Here we are using up to n tends to infinity. So for our context, it would hold for n to the power n when you go till infinity. No problem. Basically, you can, whenever you see n factorial, you can write order of n to the power n. No issues. Okay. So this is done. So this is one way to check, huh? Keep this thing in mind. There is no compulsion of choosing the denominator or numerator. Only thing is that you should see the result and accordingly judge. If it's infinity, the numerator is a steeper function. If it is 0, the denominator is a steeper function. Steeper means which has a higher growth rate. Yeah. Okay, so this was one thing. The other thing, sorry. So the other thing is, how many of you actually went through the coding of the graph topics? DFS is still okay, but topological sort and all those things. How many of you have actually gone through the coding part, not the theoretical part, but the coding part? Did you understand it? Or otherwise, if I start live coding, it doesn't hold quite well, right? So that's why I'm asking.
Sir, can you explain the complexity of the topological sorting, that how that big of n plus m can? So I didn't got it.
How, sorry, can you repeat how that big O?
N plus m. There was there, sir, the
Okay,
complexity.
yeah.
I didn't got it, sir. How like the topological sort their complexity can.
Okay, so yeah, I would definitely answer that, but the coding part, did you get?
Yeah, coding part I got, sir.
Okay, fine, no issues. I would explain that, not now. So theoretical things at the end of the session we will discuss. So before starting the live coding, I just want to ensure that the coding part where you all have doubt or anything like that. Okay, fine. So let's start then. So all of you, I hope you can see the problem on the link that I shared in the chat.
Yes, sir.
Okay. Quite easy problem. So this is for week 3 actually, since we could not do week 3 coding because of the celebration. By the way, did any one of you came to the event? None of you. Fine.
Hello, sir. Will you please send the code link again correctly?
Sorry, I cannot hear you properly. Your voice is kind of cloudy. Can you say again?
I just now joined. Can you please send the link
Acha.
correctly?
The link is shared in the chat. Please check your chat. You would see that.
In Zoom chat?
Yeah, it's in the this Zoom chat.
No, I can't see that.
Acha, you will not be able to see that, right? Okay, just wait. Yeah, please check now in the chat. I have given the link again.
Yeah, I got it.
I hope you all can see the problem, right? Is there anyone who cannot see the problem?
So it's the week 3 problem one, right?
Yeah, yeah. So any doubt in the question? If you feel someone can, if someone feels any question, doubt in the question statement, you can ask. Just one suggestion to everyone, please take care of the corner cases. I mean, the queue can be empty. What would happen when you are enqueuing or dequeuing and on an empty queue? The queue can have a single node. What will happen when you enqueue or dequeue on a queue which has only one node? And what will happen in the general case? Huh? So think of all these cases and then write your code. Some of you are not writing the code, so we would request all of you to at least try. Huh? So initially all these things would be a bit difficult. It's okay, but at least you should try. So we would wait for 5-6 more minutes and then we would start. Has anyone submitted yet? Fine. Okay, 2 more minutes, huh? Please try to complete. Some of you are quite close to complete, so 2 more minutes. Okay, anyone want to share your code, or I mean, tell something, explain it, those who have completed, or any doubt if you are facing a specific doubt. Otherwise, I will code the thing from scratch. No one? Even if all of your test
Sir.
cases might not have passed, yeah, please go ahead.
I just completed. I did run the test case. I ran everything.
Can you please tell your name?
Mayank.
Mayank. Fine. This is your code, right?
Yes.
Okay. Yeah. So, as all of your test cases are not passing, just so if your data is equal to none, return. Okay. Anyways, if queue is empty, equal to none. Okay. Temp equal to self dot head. What is this you are doing? So
So
this,
I created. I temporarily hold the head and assign the head to a new variable, new node, and then again I will the heads next will point to the temp.
okay. So if self dot head is not equal to none, in that case your temp equal to self dot head you are doing. Then your self dot head equal to node data. You are inserting.
Yeah.
Right? And then self dot head dot next. Right? Equal to 10. Okay. So in dequeue, what we are doing is if self dot head equal to none, return none. Okay, so what happens in the dequeue when you have only one cell? That is the head and the last both point to the same cell. In
Oh.
that case, getting the
So in
point?
that case, yeah.
Yeah, there would be an issue for that. Check your code,
Okay.
try to think of that case. Huh?
Okay.
Anyone else? Okay, so I checked one or two codes. Just a second. Fine. So I would code it now. No issues. I hope everyone understood the question. So only Enqueue and dequeue is the thing that you have to do. But before going into that, again a little bit of discussion. Then I would go into the coding. See, so this was again on this course. One question was asked that about queue. So a queue data structure in Python, only with respect to Python we are speaking right now, that a queue data, but it is generalizable in all most of the languages. But now, as of now, just think in terms of Python. So queue data structure, you can have it in two, you can implement it in two ways. Fine. First is by using a standard list that Python provides. Okay, a standard list, the normal list. So how will you do that? The only thing is that you can simply use slicing. The best way is simple slicing, right? For using list as a queue. What you will do is basically you would use the insert function, right? To insert at the start, let's say considering that start, I mean, if this is my list, then I'm considering that I would enter from here and I would delete, I mean, remove from here. That is, my pop would be from here, my push would be from here. Assuming this is the scenario, I would insert this 0 data, use this function to insert, and the pop function of list is already there, which actually pops, right? So you can use the simple pop function. So this is how you can use a list as queue. Also, you can simply use the slicing, right? So you can write something as L, let's say up to minus, I mean, just eliminating the last element, right? So this is also equivalent to your pop function, right? L equal to, got it? So pop function. So there are multiple ways. So in Python, in order to implement a queue, you can use it in the form of a normal standard list, which is already provided, or else in some scenarios where it is already given, like in this question, a node structure is already given and it is already implemented in the form of a linked list. It's not a standard list which Python provides, it's a linked list. So for linked list, which is my second implementation, right? In this, you have to actually define, since this is actually a class, right? Linked list is a class in which you have the head and the tail, which is the start and the end, whatever name, the head pointer and the end pointer. And that follows a specific node structure, which is defined by another class, right? So there is a linked list. So in this kind of scenario, you have to define the enqueue and dequeue, or whatever name you want to give. The normal name is enqueue and dequeue. Okay. So the enqueue and dequeue function you have to define. Fine. The basic understanding, hope that is clear. So particularly in this question, we will define the enqueue and dequeue functions. So let's start. Right. So as you can see the template code, I hope this template was already available, right? You all saw this template. So in the queue class, now we would define the two methods, which is enqueue and dequeue. Fine. So let's start. So I'm first inserting, that is writing the enqueue function. The syntax is enqueue, right? Okay. Now see, at first, obviously for enqueuing, I have to create the node. So simply I would just say it's called new node equal to my class name, which is node, and I would pass the data over here to create the new node. So now my new node is created. Only thing, now I have to insert it into the linked list, which is already there. Okay. And what are the attributes of the linked list? The first is head, and the second attribute is last. Head pointer points to the start of the linked list. Last pointer points to the end of the linked list. Head is the part where we insert data into the linked list. Last is the part from where we take data out of the linked list. Okay. And linked list works by, queue works by the property of first in, first out. Fine. So that is the idea. So head is the point where we would do the insertion. So first thing is, at first we have to check whether the list has 0 nodes, right? I mean, there were no nodes at all in the list. So what is the condition for that? I would only check whether my head, right, self dot head equal to none. Fine. Now if that is the case, then what I have to do is I have to simply allocate head equal to the new node. I mean, there were no initial nodes, right? So I simply did that. And also my last, I mean, what is the name? Next, last pointer, sorry, last pointer, that would also be my new node. Fine. Single element, only one element. Okay, so one case is done. Now what can be the other case that when there is already some node present in the linked list, so that would come under the else. Now what will happen? What are the things that we have to do? Now assume there is a node which is already, I mean, there are multiple nodes in the linked list already there, correct? And I am inserting my data at the start, at the head. That is the rule, right? For queue, my data would be inserted at the head. So what I need to do is, at first I have to, I mean, I would enter the data at my starting, so I have to change the head pointer accordingly. Or if you do it in the other way, if you insert it at the last, right? Okay, so I think here we are doing at the last, right? No issues. That accepts an integer data and insert it into the queue in the last position. Fine. So here we are enqueuing at the last position and dequeuing from the first position. No issues. So basically we would modify the last pointer in that case and insert at the head pointer. So my last pointer would be pointing to some node which is already there. I have to just change the next attribute for that node. What's the point? So my self dot last dot next, right? That I would set to new node. Now the last node's next pointer is pointing to new node, but the last pointer is already in the second last node, right? Which was already there. Now I need to just modify it to point to the new node, because by rule I know that the last pointer must always point to the last node. So now as new node is the last node, I must also modify the last pointer. So self dot last equal to new node. Fine. So either way, the only rule of queue is, here it is explicitly mentioned, right, that you should insert into the queue in the last position. Only rule is you should insert at one end and delete from other end. In case of stack, there is only one end where you do the insertion as well as the deletion. Okay.
Can you explain this part again?
Yeah.
Under the else?
I'm explaining. So what is the rule of queue? Can you tell? What is a queue?
First in, first out.
First in, first out. First in, first out, that is fine. But the idea is you insert and insert data at one end, you delete from other end. There is no compulsion that you have to insert at start always or insert at last always. The only difference is you should insert at one end of the queue and delete data or pop data, whatever you say, from the other end of the queue. Okay. And that's how you achieve the first in FIFO order, first in, first out, because you're inserting from one end, so everything would pile up on the other end, and from there you, delete the values. So what we are doing in the Enqueue, at first we are making the new node, right? Obviously we have to make the new node. Now there are two possible scenarios that can happen. First scenario is when there is no data in the linked list. There are no nodes in the linked list. Okay. So when would that happen? What is the condition for checking that when there is no nodes in the linked list? When the head pointer is pointing to nothing, right? So this is the condition. The constructor is making self.head equal to none. So if there are no nodes present in the linked list, my head and last both would point to none.
So
Fine.
we can also check the last to be none.
You can also check in this case. Yeah. Okay, but the idea is you should check, since when there are no data, both would point to none, so that is fine. But conceptually, it's always better to check for head. Why I am saying so, I would discuss. So if you write your dequeue properly without missing any corner case, then you can either check for head or you can check for last. But there is a corner case in dequeue. If you miss it, then checking for last while inserting would land you in trouble. I would discuss that. Okay. As of now, just think it's better to check with head. So self.head equal to none is the case when there are no data in the linked list. When there are no data, my node which I am inserting now is the first node which would be there. So what we will do is just initiate head and last both to the new node. Simple. No other node. So head and last both point to the new node. My new node is the first node. My new node is only the last node. So what is the other case now? When there is already some data in the linked list, right? In that scenario, what I would do, since here it is mentioned in the question that you should enqueue at the last position. On the right hand side of the screen, you can see insert into the queue in the last position. That's why what we would do is, since I have to insert in the last, let me go to that PDF. So So let's say this is my linked list, right? Okay, and this is my last pointer, which is actually pointing over here, and every list has this next one. So this is actually the next. Fine. Okay, so here last is pointing, here my head is pointing. Okay, I have a new node over here. Done, and it also has a pointer, which is not allocated to any space as of now. Generally, it's actually none currently, since I've not allocated it. It's actually none. Okay, why none? Because you see the code right here. This is none, right? Self dot next equal to none. When you actually call the node, yeah, when you actually call the node class, it's initiated with none. The next. Okay, fine. So now what are the tasks that I have to do? First of all, since I want to insert at the last, I have to put this pointer, right, point to my new node. So what is that statement? That statement is last dot, sorry, self, obviously I have to write self dot last dot next. So this is my next, right? Dot next, that should point to the new node, the last node that I have made.
Sir, this is the statement. I request you to please explain in a little bit more detail. I'm getting lost in the jargon. Self
Okay.
dot, there are two dots here. Self dot last is.
Yeah, I'm explaining. So you are saying that there are two dots, and how can we write self dot last dot next, all these things, right? How it is happening?
Yes, sir.
Yeah, sure. See, how it's happening is actually last is just a, I mean, last is a variable, correct? It's just a simple variable, which is pointing to what, when I say pointing to, what do I mean by this term pointing to? So last is basically, I mean, so in Python, you all have learned about L value and R value. I mean, the value and the memory at which that value is stored, this concept, all you have learned.
Sir, that if the set dot last dot next is the reference of the new node, right?
Yeah, that is fine. I just want to address it in a bit detail since there is a confusing point to someone. So I'm just asking, you all know the difference between a variable's value that it is storing and the memory where that value is stored. Is that clear to everyone? What is the difference between that? So when I say a variable, variable X is storing value 10. Okay, so that means there is a position in the memory, right? So maybe that memory location is something like this, right? Some typical memory location, anything. In that memory location, 10 is stored. So this is a memory block, right? And that memory block has the memory address this 0x101A, which we don't see as a programmer. That is implicitly handled by the language. In that 10 is stored. 10 is the value. So what is X? In this whole diagram, I have not drawn X. X is just an alias of this address. So to the programmer, we know X. To the system, it only knows 0x101A. Okay, so that is some abstraction that the system does on its own level. It does not show the programmer the complexity of these memory addresses. So basically, these variables are containers, which are nothing but aliases of memory addresses, and those memory addresses are that place where the particular value, as we call, is stored in the variable is stored. Fine, this is the idea. Now let's come to
So,
this.
sir, just another
Yeah.
thing. Till
Yeah.
the time we have not initialized a variable, it is just an empty container, right? It does not have a memory block as of yet. if we do
Nothing.
not-
Correct. Yeah. So in statically typed language, now what are statically and dynamically typed language? I'm not going into that. It's discussed in DBMS session. Those who are Those of you are there in DBMS, I think it's in the first session we discussed that. So statically and all of those of you have learned no need, it's okay. So in statically typed languages where you actually mention the data type, even if you do not mention the initialization, then also a memory chunk is actually allocated and some garbage value stored in that. But in most of the dynamically typed language, generally unless and until you initialize, although you would see that the variable is present, but system actually makes it, does some optimization and actually does not give memory. I mean, how Python's different versions handle that, I'm not quite sure about that. But unless and until you do some initialization, generally only the bookkeeping works happen and the memory allocation is not done. Okay. So that is the conceptual thing. Now, okay, so let's come back to the topic. So this concept is very important. Now, please, I'm relating this with this self.last.next. So what is self.last? This part is clear, right? Self.last, self we generally write when we are actually writing in the class, right? Inside the class, in order to reference the attribute for that particular object. What is the object in this case? The whole linked list, right? The whole linked list. So particularly for that linked list object, right? What is the name of that class? Queue. I mean the queue object, that means. So particularly for the queue object, the attribute last can only be referenced by using the self keyword. That is how Python works, right? When you are making something referencing a attribute of an object, you have to write self. So self.last is okay. Now what is self.last? Self.last is nothing but a variable. Just now relate this idea. Self.last is a variable which has a memory location like this, 0x whatever dot, and the alias for that is last. Okay, and it is storing a value. What is the value it is storing? We call last is pointing to the last node of the linked list or the queue in this case. So it is pointing to means it is referencing to the last node object of the queue. What is this object? This object is also a memory location, correct? It's stored somewhere in the memory. And last variable is pointing to that memory. Sorry, can you repeat? I can't hear properly. Can someone say what?
Sir, can you repeat this statement
Yeah,
again?
can you mute yourself? Someone's mic is not. Hello. So those you who has unmuted, can you mute yourself? Noise comes. Okay. Yeah. So what I said was, so last is a variable which is pointing to the last node, right? Now last node is itself a chunk of memory. It is an object which is stored somewhere, correct? Now let's say 0xAA is the address where this last node is stored, is kept. So this is your memory. Inside the memory, right, there is a part which is which has address 0xAA, and in that part the last node is stored. This last node, whatever value is there in the last node, that is stored. So this is my last node. Fine. And last pointer is pointing to a last variable, this last self.last. This self.last variable of the queue is pointing to that node. That means the value stored inside the self.last. Self.last has some other value. Let's say BC01. The address for the address for last variable is self.last is 0xBC01. That is, last variable is just the alias for the address 0xBC01, right? But the value, I told you the value here is 10. The address is 0x101A. So here the address is 0xBC01, but the value is 0xAA, which is also an address in this case. Why? Because last is not storing a normal integer value like 1, 2, 3, 4 or a string value like ABCD. It is storing the memory address to the last node of the linked list, which is itself a memory, right? So here the value was also a memory location. Okay. So when I write self dot last dot next, so this 0xAA, the value, it is also an object, it is also a node, right? So when I write self dot last dot next, this part is derived into 0xAA, then dot next. Fine. Now what is 0xAA? 0xAA is this memory location that I discussed, which is nothing but your last node. Now this actually means your last node, which is this node. Let's say I call it A node. So this actually derives to A dot next. Now if I call this is the name of the node A, then it's quite easy, right? A dot next equal to new. That's why I said the concept of this L value and R value is important. That this is the memory location whose alias is the variable name, that is the self dot last. Now self dot last is a variable which is not storing integer or string value like normal XYZ variable does in our program. Rather, it is storing the value of the last node itself in the linked list. The last node is actually a memory location. It's not an integer value or a string value. That's why the value stored is 0xAA over here. That is a memory location. And that memory location is actually the last node, correct? 0xAA over here. And that is the last node over here. So when I write self.last, it boils down to 0xAA, the value stored at 0xAA dot next. Now what is this value stored at 0xAA? It is the last node. And I know since it is a node, I can call dot next on that node. Dot next is a property of my nodes, right? So 0xA is a valid node. So node dot next. I can even write dot next dot next dot next like this. I can chain it up. Why? Because all these next are basically pointers to the memory location. And every time I'm calling dot next is ultimately means you are traveling through the memory location chain to the last node. Is this point clear? See, please clear these points, even if it takes some time. Otherwise, you would not be able to code the other questions, right? Not today, but later also. Keep these fundamental concepts clear. Can someone again tell? If you have doubt, I would repeat. No issues.
So 0xAA is the memory location of the last node or the actual position of the node, like what it contains.
Okay, last node means this one. I'm not the new node. Huh? New node is out of question now. I mean the last node which was initially there. I mean, so we told that x equal to 10 when you write 10 is the value which is stored in the memory location, right? And x is the just the alias for the address for that memory chunk. In this case, 10 is nothing but the last node. 10 is nothing but 10 is analogous to the last node. So 10 or the last node, both of them are values. Only difference is this is an integer value and this is actually an object value. Okay. So likewise, since 10 was stored in this memory chunk, same way last node itself, the whole last node object itself is stored in the address 0xAA. That is over here. Over here. The whole last node. Right? And my last variable self.last, that variable is actually storing the value of this address, which is 0xAA. Okay.
So 0xAA is the entire last node itself.
Exactly. 0xAA is the entire last node itself, and self.last is just a reference to that node. Fine.
Sir, if you show me your code, I can maybe ask a doubt.
Yeah. Okay.
Sir,
So-
here a dot next is like a function.
No. Age is just I wanted to break it down. That's why I wrote. There is no A over here. I just wanted to tell that 0xAA is, I mean, you can write 0xAA dot next and not 0xAA dot next. What I mean is the memory address, since it is the memory address corresponding to that object, you can always write a node class object dot next, right? Because next is a attribute of the node object. So when you actually write self dot last and self dot last derives into an object of node type, which is stored at 0xA memory location. So it's equivalent of just writing any object of node type dot next. That's what I wanted to say. That's why I just used the name called A to reference that. That's it. Okay. Yeah.
Okay,
Yeah.
thank you, sir.
So
I got it.
yeah. So okay. So let's go back to the code that we were discussing. Delete all this. Okay. So self dot last dot next equal to new node. So what is this happening? I'm just assigning this pointer self
We
dot
see the whiteboard, sir.
huh?
We are
Sorry?
seeing the whiteboard.
Yeah,
I
yeah,
think we cannot
I'm doing on
see,
the whiteboard only. I'm going to the code after this. Just a second.
but
So-
we cannot see where you are pointing.
Can you see now? Can you see the right that I'm picking now?
Yeah.
Okay. I think unless and until I write something, it does not show on the screen. You cannot see my cursor now, right?
No, sir.
Yeah, we cannot see.
Okay, fine. I would write it and then delete. So yeah, self, it would get a little messy, huh? But just bear with me since I have to write every time I try to point. Okay, so self dot last is this variable. It is pointing over here. Fine. So self dot last dot next when I'm saying, so that means this object dot next, this object dot next. Now dot next is nothing but this pointer, right? This pointer, next pointer. So I'm just setting this self dot last dot next equal to new node. Right, I'm just making this point to my new node. That's it. Now my last is still pointing over here, correct? Although I've joined it in the chain by putting it into this dot next, but my last pointer, which was already there, it's still pointing to this node, which is not now the last node, because now the last node is this one. So that's why I just modify it to that's it. So two things you have to do when there are already nodes available in the list. First is put the dot next point attribute of the last node, the current last node, store the address of your new node, task 1, and task 2 is move the last self dot last of the queue to the newly added node, because that's the new last node, right? So these two things you have to do.
Sir, I want to ask a thing. So this self dot last dot next creates a pointer to the new node. That pointer was not there earlier. It creates a new pointer, and that's the thing. Sir, it is creating a new pointer.
Yeah. See, so when I'm writing self dot last dot next,
it is creating a pointer. Like it was not there at first in the last node, but it
was
creates
there.
a pointer.
It was none. It was none. This statement was there, na?
Acha, it was first pointing to none, but now this
Huh.
thing is pointing to the new node.
Correct.
And
That's how you
at
actually
the last,
join.
you are just changing the position of the last to that last node which we created, that new node which
Exactly.
we created now. Okay,
Exactly.
okay. So like there is a creation of a pointer, and there is a shift of a pointer of last from that last
Exactly.
second to the last thing, new node.
Correct.
Okay,
Correct.
got it, sir.
So this one self dot last dot next will automatically store the new node reference there.
Sorry, can you repeat? I'm not clear.
In the self dot last was none before adding the new node, right?
Yeah.
Yeah.
So,
then this when we assigning this to self dot last dot next is equal to new node, the new node reference become the reference of the self dot last dot next automatically store.
yeah. So see, simple thing. The only difference that you are doing over here is initially this was none. This was nothing. So here the next part, let me write it in another color. So here the next part was storing none.
Yeah, then now we are changing to new node reference.
Exactly. So when you write this statement self dot last dot next, so self dot last dot next is this line. When you write self dot last dot next, it means this area. Fine. So you just allocate that to the new node. That means a pointer would actually, this area would point to this new node. That's the
Okay.
only thing that
The
will happen.
reference of the new node will automatically store there.
Yeah, yeah. And then you are moving the last node itself. Let's move this to here.
Sir, can you also share the problem too? Till then I can try.
Share the code, right?
No problem. Second problem.
Second problem is published. I have already published.
Okay.
Fine. So second and third is also published. You can see all those. All if you're done, you can see that. Okay. So where were we? So self dot last dot next equal to new node and self dot last equal to new node. These two things we have done. So my enqueue is mostly done. So there are no other cases. So only two cases. First case is when there are no nodes available, and second case is when there is some, either one or one more than one. I mean, there are some nodes available. Fine. Okay, now we have to write the dequeue. Oh, sorry. Okay, so since this is a queue, obviously, since we inserted at the last, we would take it out from the front. So the dequeue operation would work on the head pointer, right? So what are the scenarios that can happen? First of all, the list can be empty itself. I mean, the queue in this case can be empty. There are no nodes. In that case, there is nothing to delete, right? So you can print some statement or something like that. But in this question, it's not mentioned to print anything that the queue is empty or something like that. So it's not required. So you have to only ensure that there is some element in the queue to be deleted. If that is not the case, then I would not show anything or print anything, right? Or I would not make any changes to the queue. So how to check that? We discussed that the deletion happens from the start, and if there are no elements, then the head should point to none, right? So if there are some element, head would obviously not be none. Sorry, none. I mean, so we would check that if my self dot head not equal to none. So this is the condition where I can say that there are some elements in the queue to be deleted. Okay. Now, what are the tasks that we have to do? The first node we have to remove. That's it. So first node is pointed by head always, and we have to just remove means if I go back to the scratch pad. So this is head, right? Head is pointing to this first node. I just have to remove this node. So I can simply do that by changing head to point over here. That's it. So if I write something like
self.head.next, sir.
Yeah, self.head.next equal to the next part. That is the next node that I'm talking about, right? But one question is, if I do that, what will happen when there is only one node in the list? Would that work? I mean, you are doing self.head.next equal to the next, right? But when there is no next, it's none. So what will happen when there is only one node in the list? So that is also one case that you have to take care. So what I'm saying is, okay, just let me just write the whole thing, then I would ask. So what I'm saying is, you can just do it by writing this statement: self.head equal to self.head.next. Fine. Self.head, just making it point to the next cell. So self.head is equal to self.head, which is this one, dot next, which is this one. Correct? So yeah, but what happens when there is only one element? Then you delete that element and both of your pointers must point to none because there are no elements, right? But if you just do this, self.head is modified, but self.last is not modified. This is why I was saying it's better to check with head all the time. In this case, if you just wrote this statement, then you actually missed the self.last change in the scenario when there is only one node. So when there is only one node and you wrote this statement, the head would be modified and that would be none correctly, because self.head.next would be none in that case when there is only one node. When only one node. Fine. But self.last, you have not done anything. So self.last would actually point to the initial node which was there, because both of them were pointing to the one node, right? So if there is only one node, both last and head points to the same node. Correct. So when you deleted this, you actually modified the head one. If you just wrote this, assuming you wrote only this statement, right? But you did not modify the last one. So last would still point to this node, but head you have modified to none. I mean, absurd situation. But if you even modify last, but that is not the general case when you actually have some nodes, right? So you even cannot modify last in all the scenarios. So that's why this is a special case when there is a single node and you have to take care of that. How will we do that? If there is a single node, both self.head and self.last would be pointed to none. So what I mean is, everything would be under if self.head not equal to none. Otherwise, there is no point. So let's first check if self.head equal to self.last. If that is the scenario, that is there is only one node, in that scenario what we would do is both would be pointed to none.
Sir, we can also check like that if self.head.next is equal to none, then self.last equal to none.
Yeah. You can just, you have to consider in any way you can check.
Okay, sir.
You just have to consider all the cases. That's it. Okay. Else the normal case where we just do self.head equal to self.head.next. Okay. Now one thing is there, it's okay, we have no problem in the code, but only one thing is that it should also return the deleted elements, right? The question is asking you to you should delete as well as return the deleted element. Now since I have already changed the pointers over here, I cannot go back, so it's better to actually keep a temporary storage of the data at first before you change the pointers. So what we would do is, we would just store some value, right, in the some variable item which was already there, and we just put the data into that, the self.head.data, because we delete from head, right? Okay, so we put that data over here, and at the end we just simply can return the data, I mean the item. Fine, we can do something like this. Okay, so where did we miss? Enqueue is done. Oh, spelling. DEQUEUE. Fine. Okay, so before moving to the other question, any doubt, please ask. So I just want to give more time on the fundamental concepts. Again ask. So we are seeing discourse post on, we are facing problem on programming and all. The idea is once you clear the fundamental part now, it would be very easy for you to think about complex code. But if there is doubt in the fundamental idea, that this question was very nice, how we can go self.head.next. So those who have done some coding, it's easier for them. They all can move to the next question. And if someone has already done the two other questions, I would again publish the other ones as well. But those of you who are new to coding, please clear the fundamental doubts. Otherwise, as the week proceeds, you would not be able to code the complex codes. Fine.
Excuse me,
Again,
sir.
yeah. Any doubt, please ask.
Sir, I had a general doubt regarding the self argument. So,
Okay.
what does actually the self argument refer to? Is it a pointer in itself sometimes, or just something we use to refer to in a class, which we have to?
Exactly. It's a pointer. It's kind of a pointer to the current object under use. So I can have this queue class is there, right? So I can have multiple queues. I can just write queue open parenthesis close parenthesis, and that would create multiple queue objects. Correct. So self, whenever I'm writing these functions, self, or whenever I'm writing self as a in the functions of the class, that actually means this self refers to the current queue under consideration. What does that mean? That means if I'm calling Enqueue, right? So let's go to this part of the code. A equal to Q. This is the object created for the queue. Then I'm calling A.Enqueue. I'm calling A.Dequeue. So the self actually refers to this A object. Okay. When I'm calling A.Enqueue, it means self.enqueue, something like that. Fine. So the self variable actually is a kind of internal pointer which points to or refers to the current object of that particular class under consideration. Under consideration means the current object which is being used to call the methods of that class that you are calling right now. That A.Enqueue, that means self is actually referring to the A object.
Okay, sir. So when the code is running, it actually kind of will be like A dot head, A dot self, A dot
Exactly.
next.
It's kind of that. Internally, it's like that. There are some other aspects as well, but yeah, for understanding, it's correct. It's kind of that only. So, so if you see other languages like Java, or let's say C class concept is not there. I mean C++ or Java. So in those languages, this is actually implemented or used by using the keyword this. Those of you are familiar with Java or C++, I mean, you use the keyword this. So Java, this is a pointer. C++, this is a pointer which stores the current reference to the reference to the current object under consideration. Okay, in Python we call that self. Fine. So any doubt with respect to this queue thing? Any algorithmic doubt, data structure oriented doubt?
Sir, in the 23rd line, why did you add the dot data in the end?
Which line? Sorry, can you repeat?
23rd line.
23rd line.
Dot data. Yes, can't it be only self dot head?
I mean, we just have to return the value. No? See, the question is asking you return the deleted element value. Deleted element value. So I have to return the value which was there. So value means the data, right? It's not the pointers or anything. It's the data, the entity which was there. So that's why I'm just storing that into a temporary variable called item and then returning that. That's it.
Okay.
So that's why we even did not write this line at first. I mean, I did not see this part. So only your deletion dequeue would be this part. This is correct. This is your dequeue. Fine. But later I saw that you have to also return the value. So before you change the pointer, you store the value into a temporary variable called item. And once the dequeue process is done from line 24 to line 28, at last you just return the initially stored value. That's it. Because it's asked in the question. So this is the data or the value. Okay. So now let's go to the second question. All of you, those you have started working on the second question, fine. Those of you did not, please try to do the second code. And yeah, maybe after 10 minutes, we would discuss the second question. Not 10 minutes, at 35, we would discuss. Even though you couldn't, I mean, those of you were engaged in this question till now, you would not be able to complete it, but please try to do the part as much as you can for the second question as well before we start discussion.
Sir,
Yeah.
this add last or those are inbuilt functions
Which one? Add last means?
as head last
No,
data.
no, no. So this class, right? See this class. Node is the node. Right? There is a class which is the node class. Fine. And the node class has a constructor. That constructor actually has two attributes, data and next. So which actually defines your node. So which means this is your node class object. Node class object. You all learnt about classes and object in Python, right?
Yeah.
Those who have done Java, anyone done Java or is doing Java parallelly?
Yes, sir, I am.
Okay, so those who are in Java or I mean are doing Java or have some experience of in Java or any language, they would be very familiar with this concept. But even in Python, I hope you all have done classes and object. So when you write node class object, so this actually has one data and one next part. Okay, so if you go over here, this data and next.
Okay.
Fine. And I'm using that node object. I'm using that node object to make a linked list of these. That is, make linked list of these objects.
Okay. Thank you.
That is done using this class queue, linked list or queue, whatever. So head last, if you see, when I'm enqueuing, that is I'm putting a value, that value is a node object, right? See, when I'm enqueuing or putting a value, that value or my new node is itself the node class object. When I'm calling the constructor over here of this constructor, right? So it's like a array of, I mean, you all are familiar with the array of objects, right? So this is a linked list or queue of objects. Now, what is that object? That object is the node class object. Clear?
Yeah, clear.
Yeah. Okay.
Sir, I have a doubt about question 2.
Okay. Wait. Question 2.
Sir, most of my code was written for me from before.
Let me just check it.
Or am I going to the wrong repository? Oh, I'm doing on week 1. I'm so sorry. I'm so sorry, sir.
Okay. Yeah. Okay. So your question 2 would be, okay, did I not publish it? Yeah. So it's on a doubly linked list. All of you can see the second question, right? In your own, it should be visible. Second, third as well. Yeah. So those who have completed second can move to third. Okay, so one code actually, I mean, many of you could have done it, but even if some of you could not understand it, it's totally fine. We would discuss it. But I can see one student's code is working fine and it's running all the test cases. So I would take that case and then we would discuss. Fine. So its name is Lakshmi Nandan, huh? Yeah. So your code is working. Can you please respond, Lakshmi? Is it you? This is your code, right? Are you there?
Yes.
Yeah, sure. Okay, so see what is asked in this problem is, so let's discuss the problem at first. Okay. So there's a doubly linked list. So every node in the linked list would have a next pointer and as well as a previous pointer. Fine. So you can travel both ways. Initially, you had only one pointer which was pointing to the right hand side node, which we call the next pointer. And now you have both the next as well as the previous. So you can, from a given node, you can actually go to the next as well as the previous nodes. So what you have to do is you have to write a method called insert at position, insert at POS, that where you would give a data and the position, and you just have to insert a node at the given position which would contain the given data. That's it. Fine. Using a doubly linked list. So in the question, you can see the template a node is given just like the previous one. Only thing is here we have two different pointers, next and previous. Okay. And you have a doubly linked list head and last just like the previous question. No other differences. Only you have to insert it at a specific location. So my question before going to this is, go here. So if you have to insert a node, let's say, fine, this is the position where you have to insert a node. Okay, fine. And here you already had one node, correct? And you want to just push this node this side, and here you would actually, in place of this node, you would actually insert another node. So my question is, on which node you have to come and then do your operation? Although you have both left and right, so you can go either way. But generally, if you have to insert at this position, now you come over here, right? And then you modify this next value to the corresponding new node that you want to create and put. Okay, change the next pointer to that new node. And before that, this next part, it is actually pointing to this node, correct? And you must not lose it. So what you do is initially, you store this next part into a temporary variable. Okay. Once you do that, after that you modify this next to store to your new node. Okay. And also you have to put the new node's next part point to this one, because that should continue. The chain should continue, right? And erase this. This you can get from the temporary variable from where you stored the data, right? This data, next pointer. From there you can store it over. Okay, so I'm just making it again, writing it. Step 1 is store next into a temp variable. Number 2 is point next to new node. Third would be point next of new node or if you want to put this one first, then point the next of the temp to new node. Either way. Okay. Okay. Doesn't matter. It depends on you what you want to implement. So this is the idea, and also you have to accordingly modify the previous pointers as well. Okay. So now let's go to the code and then discuss. So I'm not discussing these templates. This was already there. So a node class, just as discussed earlier, and a doubly linked list class which has head and last. Okay. So insert at end function is already defined for you. You don't have to do anything, but that's not required also. I think you're not using that anyway. Fine. So this is the function which you have to write as written by Lakshmi. So see what we are doing here. At first we would generally normally create the new node. Fine. Once that is done, we have to check whether the list itself is empty. I mean the node the linked list, whether that is empty or not. So we are again checking if self.head is not none. Right, it's not none. There are some elements at least. Fine. Then what we are doing is in that scenario, we are setting, see, we discussed about temp, right? At first we have to store the temp at some position. So I'm storing self.head in a temp. Now see, we discussed that you have to reach that particular node where you want to insert the value, right? So in order to do that, you have to count the number of positions that you are traversing on the linked list one by one. And until you reach to that particular node, after which you have to insert the value, I mean, after which you have to insert the new node, you have to go on doing dot next, dot next, dot next. Fine. That is how you traverse a linked list. Simply traversing the linked list up to the point after which you would insert the new node. That's the idea. I'm just repeating again. You have to, in order to insert a new node at a specific position, you have to traverse through the linked list up to that node after which you want to insert the new node. Okay. And in order to do that, since you are doing dot next every time, you are simply running a loop. Okay. So this is the while loop. And I mean, he's using a variable ptr equal to 1, and unless and until this ptr grows up to the position -1, we are incrementing it. Simply just doing temp dot next position number of times, position -1 number of times. Fine. So that's done. Now we are at the node before that node where we want to enter that our new value. And then we are simply doing temp dot next. We are storing into another temporary variable called nxt and setting the previous value to the new node. I mean the node that we have created now. Correct. Setting the next value to that temporary. I mean, you have to read it. I mean, it's unless and until you understand it, even if I say it would not be clear, you are just basically setting the previous and next of all the variables at that point where you want to insert the node. So the left node from your new node and the right node from your new node, you are just setting the previous and next. Fine. Read it and then ask your question. So that is the idea. You are simply traversing. You are simply traversing to the point where you have to add the new node. This is the while loop. Okay. Now once you have reached at this point, now just you have to do is you have to adjust the previous and the next of these two nodes. These two nodes. That's what you are doing. Okay. So let's go to that code once again.
So if we have to insert at fourth position, we have to change the next of the third one, right?
Yeah, exactly. That's what I'm saying. So you have to change the next, now the third one, which was initially at the second one, right? Since you have inserted one, so it's the third one after that.
So here, what is PTR denoting?
Sorry?
PTR.
PTR is, see, you have to travel to that point where you want to insert the value, right? So how would you count? So this is just a counting variable. PTR is a counter which you are initializing with 1 and then incrementing every time unless and until it goes to the value of position -1, because you have to actually reach to that node, that is the position, correct? That's it. PTR is just a counter variable which is counting the number of times you are traversing to the next node in the linked list.
If we will remove this PTR, sir, then I think that the code will.
How would you reach to this point now? See, your head is over here. Your head is pointing over here. Just a second. So this is your linked list. This is the position where you want to insert your data. I mean the new node, right? In this place. Correct. So your head is pointing over here. Correct. And your last is pointing over here. Now every node has 2 pointers which they are pointing like this. Previous and last. Sorry, next. Now you have to reach, I mean, you have to delete this, sorry, not delete this, you have to insert the data at this point. Do you have any pointer directly to reach at this point? No, right? You only have head which is at start and you only have last which is at last. So in order to reach this point, you have to travel like this. And then when you are over here, then you modify the next of this variable by, I mean, inserting the new node and all. So you have to travel this much, these 2 hops. So that is the position -1. So this is the position. This is the position -1.
Yes, this is I am understanding, but sir, PTR.
How would you reach? You have to increment some variable PTR plus plus until and unless you reach the value of position. You reach position -1. Do the pointer that he used. What is the name of that pointer? Temp, right? Temp dot next. So how many times?
Yes.
How,
yes, I understand. Got
okay.
it.
How many times?
Yes.
That's the question. How, in order to know how many times, you have to have a counter variable that would count each iteration and you would proceed one hop, up to the value how many times position -1. So in order to do that, he is using a variable called PTR. I mean, in order to make it a little more conventional, you can call it counter plus plus. That's it. Right?
Yes. Yes. Got it. Thank you.
Fine. And after that, you are simply setting the, once you have reached the place. Now this part, I mean, it's better to read and understand rather than me actually asking. If you have any specific doubt on a line, I can discuss. It is just simply once you have reached the point, you store the current value of the next into a temporary variable, right? See, temp dot next into a temporary variable. This next is the temporary variable now. And then you insert the new node, this new node, right? And once you have inserted, you set the next value of the new node and the previous value of the new node accordingly. That's it. So this is just setting the previous and next of the nodes at that point. Fine. Any doubt?
Sir, two questions. One was, so indexing does not work, right? Anything like data square
No.
bracket POS minus one, that
No,
will not
linked
work.
list you cannot index, right?
Okay.
Yeah.
And the second question was, sir, we also have to change the next of the previous element and the previous of the next element.
Yeah. Both you have to change, right? Because there is a doubly linked list. So you have to change both
Right.
next and previous.
So where is that happening in this?
Sorry, can you repeat? There is?
So where is that change happening in this code?
Here the previous and next both are changed, right? Which one you are asking particularly?
So the variables that we have before and after the new variable, we have to change the next pointer in the previous variable and the previous pointer in the next variable. Where is that changing? I was not clear about that.
Okay. So let me just tell it. So NXT is the new place where you are storing the current temp.next. I mean the current, which was the variable. Okay, then you are storing that NXT dot previous, okay, equal to the node. That is, this NXT is okay. This NXT is this new node, right? So this is my NXT. According to the code, this is the NXT, and my new node is somewhere. My new node is this one, right? And then what we are doing? I'm setting the NXT previous to the new node. So I'm setting NXT's previous, I mean this part left side, to the new node. Okay, then and I'm setting the node dot next, the new nodes next to NXT. That is this next, right, to NXT. I mean, so the previous part, so I am assuming this node is over here and this is over here.
Correct.
Getting the idea? I mean, this new node is over here. It's located over here.
Correct.
Correct. Got the point?
Yes, sir. Now I got it.
Yeah. Just you have to just think about it. Same thing. Okay, so it's a little bit getting late. So those of you have completed this, and no doubt, please move to the third question. I hope I have also published the third one. Let's check. Yeah, third is also published. Let me just publish both 1 and 2 as well. Okay, so one more thing. Okay, so those who have started the week 3 problem 3, you can continue with that. But those who are trying to start now, I would request you to do the week 4 problem 1. So at least we had some discussion on stacks and queue. So let's have at least a few little discussion on the graph. So week 4 problem 1. Now those of you who have started, please, try this one first. Week 3 problem 3, you can do a bit later. So since we don't have a lot of time, around 8 o'clock, we would discuss the problem 1, week 4 problem 1.
Sir, is it possible to have one more live coding session over the weekend or early next week?
Yeah, we were also thinking something along the similar lines. Yeah. So any specific topic or anything or coding only you want?
So live coding will be helpful.
Okay, fine. We would do live coding. So let's do one thing. So we would discuss the coding part, not the, I mean, not the theoretical aspect only. So most probably we would do some coding as well as the dry running of the problem. So you all know how topological sort works, how BFS, DFS, pre-post numbering works. But let us do some coding, parallelly do a dry run of the algorithms and see how which part of the code corresponds to the dry run of the algorithm. When you run it on pen and paper, which part of the code is actually doing that? Okay, some discussion on that, and then we would do some live coding also, some problems as well. Right. So on Saturday or Sunday, we would check the availability and then we would inform. Right.
Sir, we try to Sunday.
See, that's not, I mean, we also can't say confirmly. So let us check and yeah, we would try if Sunday is available. We would try for sure.
Okay, sir.
Any one of you have any live session from 8 after this?
Yes, sir, TDS.
Okay. Okay. So let's take 1 or 2 more minutes and then we would start discussion up at 8:02. Okay, so due to lack of time, I would start the discussion. So let's discuss first, and then I would ask if someone has done it, or else I would code it up. So first of all, one question, and I want someone to respond. So can we use DFS to find the shortest path? So BFS and DFS, both of these are algorithms to traverse a graph, right? In order to traverse a graph from a given node to the other nodes. So my question is, path finding can also be done using DFS, right? Whether a particular node is reachable or not, that is also doable using DFS algorithm. So reachability check can be done with DFS, or we can't do. Only BFS is compulsory to check reachability. The question is, can we only use BFS algorithm to check reachability of a node, or DFS can also be used to check reachability in a given graph?
So both can be used.
Both can be used. Fine. So what is the advantage of BFS then in order to check reachability or in order to check path?
Sir, BSF give the shortest path.
Shortest path. Fine. Can you comment a few lines on why is it so? How it gives the shortest path? I mean, what is the intuitive difference between both of them, because of which BFS is able to give you the shortest path? Okay. See, the properties of an algorithm. Yeah, please go ahead.
Yeah, in BFS, you check at each level. You judge the level, then you move.
Correct. Yeah. So BFS will actually proceed by level. So unless and until it explores all the nodes of a particular level, it would not proceed to the next level. What do we mean by level of a graph? Level means the number of edges at a particular state. I mean, so let's say there are 3 nodes in a graph which are a single edge apart from the starting node. So I would say these 3 nodes are 1 level away from the starting node. Fine. Let's say there are 4 nodes. Yeah.
If you're writing anything, your screen is freezed, it seems.
No, I'm not writing. I'm just saying.
Okay.
Fine. So level means, okay, since you said, so if we have a node like this, I don't know, maybe something like this. Okay. And this is my starting vertex. Fine. So this node is one edge away. This node is 1 edge away. This node is 1 edge away from my starting vertex. Correct? So all these 3 nodes are level 1. Okay. Or I mean, depending upon convention, anyone, we can start with level 0 also, no issues, but idea is 1 edge means level 1. Okay. So what are level 2s? All the nodes which are 2 edges away, minimum number of 2 edges away. So let's say this node, this is 2 edges away, right? 1 edge, 2 edge. So 2 edges away. Even from this line, 1 edge, 2 edge. So minimum number of edges, huh? You can't consider the maximum one. Minimum number of 2 edges away. So this is at level 2. Okay, so this is again at level 2. This is also level 2. So violet colors are level 2 edges. Sorry, level 2 nodes. Okay, so that is the idea of level. Now BFS proceeds level by level. That is, unless and until it has pushed all the BFS uses a queue, right? So now if you see the programming part and relate with it, unless and until the BFS algorithm has pushed all the nodes at a specific level, it would not go to a node of the next level. That's the idea. Now, if that is the case and levels are decided on the basis of number of edges away from my starting node, that is basically the distance, right? So that is basically the distance from my source. So BFS proceeds each level by level, which ultimately means it proceeds each edge by edge, and that's why it gives you the shortest possible distance. Fine. Shortest possible distance means here the consideration is the graph is unweighted. That is, all the edges are of equal weight. It's just like a single hop, one jump you are doing. There is no specific weights associated with the edge. That is, the edge only represents equal distance away, which you can also call a unit away. Fine. But next we would learn in the subsequent weeks where the graph edges have specific weights associated with them. That means the distance, the idea of distance comes. So this way it would be longer, that way it would be shorter. In that kind of scenario, we cannot use BFS to find the shortest path between the source and destination. Fine. So as soon as the graph edges becomes weighted, we actually look into some other algorithms called the Dijkstra algorithm, Floyd-Warshall algorithm. Those things are there. The Bellman-Ford, those things were there. We would learn it. But until it is a single hop where the edge weights doesn't matter, BFS gives you the shortest path. DFS cannot, because DFS runs arbitrarily. It would just run arbitrarily in any distance unless and until it gets into a dead end and come back. Right? That's why DFS use stack. So you just put each stack one after the stack. In the stack, you would put each frame one after the other. As soon as you see that there are no other edges available, so in the same graph, if I do DFS, okay, since we are already late, I'm trying to cover some topics. Anyways, you can, so those.
BSF is used only for non-directed graph.
Yeah, BFS DFS is generally for, I mean, can do directed graph, but generally it's, I mean, you have to modify some part of the code depending upon what you want to do.
Sir, I think we perform DFS in directed graph for finding acyclic, but we
No, it would be problem. Yeah, you would run into problem. If you use BFS or DFS in directed graph directly without, I mean, there is a way to find cycles in, I mean, sir has also taught that the pre-post numbering, correct? So you can use BFS, DFS, but with pre-post numbering, then you can find cycles. But if you generally in undirected graph, you can use BFS DFS, even without using pre-post numbering, you can find cycle in undirected graph. Fine. But in directed graph, if you apply the same technique, it would not work. In directed graph, if you are using BFS or DFS to find cycles, it's important to use the pre-post numbering method that sir has taught. Okay. Fine. So how DFS would
also
work?
connectivity.
Yeah.
For directed is a graphs. Can we find connectivity by use of BSF?
In a directed graph, can you find connectivity using DFS or BFS?
Yes, sir.
Yeah, you can do that, but again, there are some changes that you have to do. It's not the direct code, right? Because see, this cross edge, forward edge, all these things you know, right? So you have to judge all those things, that whether there is connectivity or not. So if there is a cross edge and there are no other edge to that particular node, then actually you cannot reach to that node. If you have started, so let's say, fine. So this is my graph and my starting vertex is this one. Obviously, if it is undirected, then the graph is a connected one. But since it is directed and my start vertex is this one, I would always go like this, but I cannot reach this particular vertex. The reason for that is we have an edge, but the edge direction is from the other way. So I cannot reach here. I cannot reach here. So it's unreachable. So this edge is actually kind of a cross edge. You can say it like that. So what is cross edge and all? I mean, that's a theoretical discussion. Sir has taught that. If you want, we will also do it in the Sunday or Saturday session. Again, by using the pre-post numbering. So pre-post numbering, a cross edge is one where the part, I mean, where there is no overlapping. the pre-post of the two vertices for a cross edge. So if I say u comma v is a edge, right, between u vertex and v vertex. So in order for uv to be a cross edge, the pre-post of u and the pre-post of v are non-overlapped. There would not be any overlap. They would be disjoint. Fine. So if this is the scenario, in this kind of scenario, if you do simple BFS DFS, it would give you connected, right? But actually it's not connected in that sense. It's connected, but you are not reachable to this point. So depends on what you want to check. If you want to check reachability, then in order to check reachability and connectedness, you have to use the pre-post numbering along with BFS DFS, right? But if you just want to see whether there is a single edge, I don't want to see reachability. I just want to check if it is connected by any edge at all. If that is the definition, then you can use BFS DFS. Just assume it like undirected graph, no problem. Okay, so that depends on what you want to do, but generally you have to modify using the pre-post numbering in order to do this kind of work with BFS DFS. Fine. Okay, so we were discussing about this DFS, right? So DFS can proceed in arbitrary way. So let's say you go over here, then you go over here, okay, then you come over here, and then you see that I have already visited all the vertices. So you just unwind up to this point, and then you again start over here, 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 and again you see that I have already visited, since the next would be this one, but you have already visited this vertex already, right? So you would again unwind over here and then move out of the stack. That's how DFS works. So DFS would actually run like a mad ox until and unless you get a dead end. Once you dead end means where a vertex is already visited, that is a dead end for DFS, or there are no vertex at all, either of these two. So when you reach that dead end, you actually pop the stack frame one by one and reach to a point where you can take another path. If there are no path left, you just move out of the recursion. So that's how DFS works, and that's why DFS is a stack. Okay, so DFS cannot give you the sense of short distance, it can give you the sense of reachability. BFS can give you the sense of reachability along with the minimum distance. So I discussed this in a bit more detail than required. The reason for that is here the question is asking you for minimum number of hops required. Okay, we are not telling you BFS or DFS or anything. You have to understand that you have to use the BFS algorithm in order to find the answer. Okay, so I'll just code it up. So what we have to do now, see, there is a starting vertex which is given 8 in the sample input, and the ending vertex which is the 7th vertex in the input, and we have a array list, adjacency list, where the graph is given. I mean the normal connected network, the graph is given in this manner. Okay, what we have to do is we have to find the shortest distance, that is the shortest number of hops required to reach from the start to the end. That is the question. Now we know that the answer to that is BFS. We have to use BFS and we have to generate two lists. The first is my parent list, and second one is the you call level list or whatever you want to call, that where you would get the number of levels away a particular node is from the starting vertex. And parent is that list where you would get from given a particular node, what is the previous node in the path, in the shortest path, I mean, that you would actually encounter on the shortest path. Yeah, so given a node, what is the previous node to that node on the shortest path from the start to end vertex. So these two lists we require. Once we find these two lists, then we can just backtrack on the parent list, right? I mean, the list which stores the information regarding the parent of every node. What we would do is we would simply go to the destination, which is end equal to 7 in this case, and we would say who is the parent of 7. Then whoever the parent of 7 is, we would again say who is the parent of that particular node. So we can check iteratively or recursively, anyway. We can check the parents until and unless we go up to the node 8. Once we get 8 in the path, we would stop the iteration and we would say, so this is the shortest path. Fine. So that is the idea. So in order to do that, we have to have the parent list at first. and that we would get by using the BFS algorithm. So see, since we have to call the BFS algorithm, so let's write BFS. We would define the BFS function. Okay, and obviously I need to pass the A list into the BFS and the starting vertex, right, from where I have to start the search. Okay, so this is the idea. I have to call BFS, pass the required parameter, which is the adjacency list and the starting vertex. This BFS should return me two important lists. The first one being the parent list from where I would get the path, and the level, that how much away it is, right? So level list. So I would, let's say, call it level comma parent, or let's say path. It's better. Okay, actually getting the path from here. So path list and parent level list we get from the BFS. Fine. And then after this over here, sorry. Fine. So before going to that part, let's now define the BFS. Okay, so BFS and let's say my start. Okay, so I'm starting from the initialize the two lists that we require, sorry, the two dictionary that we require. The level, okay, I have been saying list as of now, that I mean the dictionary, which where you would store the list and the level and the path, right? So level comma level equal to, and my, so here let's call it parent only. Okay, I have two dictionaries. Now I have to initialize them. You know the normal BFS, this is just like normal BFS. Okay. List dot keys. Fine. So next I have to initialize the level. So level would be -1, level of I, and my parent is the name, parent of I is also set to -1 initially. Okay. Acha. Also now BFS requires you to have a queue, right? That's the next thing that you have to think about. So I told you that queue you can implement in two ways in Python. Either you can have a linked list, which is already given, in which you have to define the enqueue and dequeue functions, or you can simply do it in the form of a list. The only thing you have to take care that you should push at one end and pop at other end. And yeah, that's the only thing that you have to take care. So I would use a simple, the Python list in this case, in order to make a queue. Fine. So let's call it a queue. Okay. And yeah, so now my BFS start. This was my initialization. What is BFS? At first I have to use the start vertex and put it into the queue, right? And in order to do that, I must reference the start as the level 0. So my level of start is 0, and then I would put it into the queue. I'm simply, since I'm using the rear end as insertion, so I'm using queue.append and the start vertex. Okay, so first vertex into the queue given. Now what I would do is, what is the, how BFS works is, you would push, you would pop each vertex from the queue. You would check whether that is whether the neighbors of that is visited or not. If the neighbors are not visited, you push it into the queue and you continue the algorithm. And you have to set the level and parent and all those things in the process. So basic thing is, pop from queue, check the neighbors. If the neighbor is visited, leave it. If it is not visited, push it into the queue, set the level and parent of that particular neighbor. That's the only thing that you have to do. How many times you would do it? You would do it until and unless your queue becomes 0. I mean, there are no elements in the queue. Fine. So first thing is we have to repeat the process, whatever we are going to write from line number 10 up to the number of times, n number of times until and unless our queue becomes empty. So how can we check that? Simply, since this is a normal list, just check whether the list is empty or not, or you can use the length function or whatever. I'm just using the length. So while my length of queue is greater than 0, up to that point I would repeat the steps. Fine, until and unless it becomes empty. Pop from the queue. Next step. So let's say I used to call it element or item. Item or item kind. Item equal to my queue dot pop. Now the list pop actually uses an index, right? As you can see. So obviously, since I am inserting on the rear end, I have to take it from the front end. So 0. There is no compulsion. If you do it the other way, that is also fine. Only thing is the idea should be clear. So q dot pop 0, the first item I have popped. Sorry. Okay, now next is check the neighbors, right? So for neighbor, it's getting long. Okay, for k in say my list, right? Small l, right? Yeah, a list. Okay. So for k in a list, for the adjacent, I mean, you are checking this for the particular node we have popped, right? That is my item. Fine. So all the neighbors for my item, the node which is corresponding to the item that you have currently popped. So all those neighbors I am checking if they are visited or not. Okay. So see how to check visited. Now you remember in the lecture Saras taught us, initially you can use a visited dictionary in order to check whether a particular node is visited or not. But if you are using level itself, right, then you can simply check whether it is -1 or not, because initially you have initialized level equal to -1. So everything which is yet not visited, the level of that would be -1. So simply checking whether level is equal to -1 is equal to checking whether that is visited or not. Fine. So I would check if level of the k element is equal to -1 or not. Now if that is the case, if that is the case, you got -1 for that level, that means it's not visited, that neighbor is not visited, then I would just increase the neighbor, like the value of that level by j plus 1, right? Because it is coming from the jth level. So level of the item from which I am the popped item, right? So popped item plus 1. Done. And so level is set. Next thing is I have to check for the parent, right? Parent we have to set. So parent of k, since I am taking it from item, so item is my parent. Okay. And yeah, so these two things are set. It's not visited, that's why we would append it into the list, the queue. So queue dot append my k. Okay. So simply check for neighbors, check if it is visited or not, which is done using level in this case. And if it is not visited, append it to the queue and set the level and parent dictionaries accordingly. This is extra thing that we are doing because of the requirement. The core BFS actually is this part, line number 12, 13 and line number 16. Okay. So I'm appending it, and yeah, so this would run until the queue becomes empty. and then simply return the list, I mean the dictionaries which you have created after exhausting this whole while loop. So that would be my level. Okay, where I am storing it? Yeah, level is first. So level and my parent. Okay. So this is the plain BFS algorithm, and now we would come back over here. This is the next thing that you have to do. We have to find the path from start to end using the iterations on the path list. Not path list, path dictionary. Okay. So this is the next task that we would do. Because now we have the path. I mean that you have a dictionary in which you have for each node you have the parent. But now you have to find the start and end, right? So you would just have to iteratively check who is the parent, who is the parent, who is the parent, one by one until you get to the start vertex. Okay. So let's do that. Yeah. So at first I have to check. I mean, I have to store it, the path in some the minimum path that I'm getting into some area, right? Some place. So let's call it the shortest path, S path. Okay. My S path list in which I would store. And next thing that I would do is, see, there can be a possibility. See, if you see this question, right, at this point, return the list with only start if the end is not reachable. Correct. So whether the end is reachable or not, that you don't know. You have to reach the end, but you don't know whether that particular graph which would be given in the test case, in that the end is even reachable or not. If it is not reachable, then what you have to do is you have to only return the list with the start. Fine. And if it is reachable, then you have to actually check the shortest path that you can get from the path dictionary. So I would only check for shortest path when my end is reachable. When can I say my end is reachable? That means end, the node corresponding to the end, which is 7th in this sample input, that should have been in the queue, right? That if it is in the queue, see, if it is in the queue, if a particular node is in the queue, that means it is a neighbor of a particular node, and then only I am going to append it, right? This queue.append would only happen when it is inside the for loop, right? Because this statement is a part of the for loop. Correct. And also if it is a part of the if statement which checks if level k equal to -1 or not. Fine. If it is -1, then it is putting. So I would just check that fact only if the level is actually not -1, right? That means you have already put that into the queue and you have visited that. You have visited that means it is reachable. So my condition for checking whether that node is visited or not or reachable not is simply check the level. If level of the last node, right? What is the variable which is the destination? End. Okay, so if my level of the end is not equal to -1. In this scenario, I know that I have actually reached the end node. Fine. If this is the case, then I would simply now iteratively I would just run a loop and I mean I just go through the loop and put each parent one after the one. Just see what we are doing. So what is the name of that path? S path, right? S path dot append the last vertex I'm appending now, which is the end in this case. Right. Now I would just run the loop up to the point unless and until I reach to the starting vertex. Okay. So I would check while the S path that I have, the list that I have got, that does not contain the start. I mean the last node of that does not become equal to the source vertex, which is the start vertex. Okay. So if this part is confusing for someone, what we are only trying to do is we are having a path and that path is the, I mean, we are just appending each node to the path from using the parent dictionary, or in this case the path dictionary, right? From the end to the start. That's it. Fine. So the next statement of this could be, now I have already at one level down, so I would just check the next parent in this case. So it would be my end equal to the current parent of end. The parent of end is stored in this variable, right? The path dictionary stores the parent of each node. So path end means the parent of the end node, and that I am storing into the end itself, because that is recursively moving, right? Or iterative. In this case, it's iteration. Yeah. And I would simply add the end now into the same path, because there is a next parent. So next parent is essentially the next node in the shortest path. Fine.
So can you explain this while loop again?
Yeah, I think it got a little bit. Let me complete and I would explain once more. Fine. It's simply thing. Just you can. What we are doing is we have the path, right? So we have the path. The simple thing we are doing, you can also implement on your own. Then you would understand. So this is my path dictionary, right? So here we have the nodes, and here we have the parents. So A, B, sorry, not A, B, C, D. 0, 1, 2, 3, 4, whatever, right? And here we have the corresponding parent. So let's say 1 is the parent of 0, then it's 3, 4, 2, whatever, right? Something like this. So now we know that start is, suppose the start is my start is 3, fine, and my end is say 1. I don't know whether it would work also. So we would check 1 is the end, right? So 1 is the destination. I need to get the path from 3 to 1. So what I would check is who is the parent of 1, right? I'm going over here. I'm checking 1 is there. Oh, sorry, 1 is here. The node 1 is here. Parent is 3. So that means in order to reach 1, I have to reach 3 at first, and then I would reach 1. Fine. Next, I would again see who is the parent of 3, because 3 was the parent of 1. So this is equal to, so 1 was the end, right? Sorry, my voice is getting a problem. 1 is the end, right? The parent of 1, see this statement only I wrote, right? Parent of end. Here end is 1 now. Parent of end or parent of 1, sorry, 1 was 3. 3. So this is equal to 3. Okay, so I got that. Next step is who is the parent of 3? But I don't need to check that, because we have all, see, start vertex is 3 already. Fine, we have reached 3. So I can just answer 3, 1 is the direct path. But let's say 3, 1 is not the direct path. I want to start from 2. Fine. So the next step that I have to do is who is the parent of 3? In order to check the parent of 3, I have to again, I mean, set the end to be 3, right? So, see, end was the value which was earlier 1. Now I check the parent of end, which is 3. Now again, recursively, I have to check who is the parent of 3. So since I've already written this line of code, I can just use a loop to execute this line only to find the next parent in the path. But in order to do that, I have to change the end. So that's why I'm just changing the end equal to parent of end. That is the idea of this line. This line. Only the name is path over here, not parent anyways. So end equal to path of end. Okay. This line means this, because end is 1 over here. The parent of 1 is, I am storing that into end again, and simply I would execute this line only multiple times using the loop, and this would work. How many times? Unless and until I reach the start vertex, which is 2 in this case. So how can I check I have reached the start vertex? That is the if condition that I write over here. Na? See, while S path last entry is not equal to start. That is the in the path, the last node in the path is not start. Until and unless it is not start, you continue. Once it is start, that means you have reached the start vertex. So you stop the process. Okay, simple thing. Just read these lines, you would understand what we are doing. You are iteratively checking the path dictionary from the end vertex to the start vertex. That's the only thing that you do. Until and unless you reach the start, which is this while loop.
Yes, here so you're appending, so every time it is appending towards the end of S path, and the moment the end becomes the start, it will stop.
Exactly. Okay. Okay, so we have actually created the path. Am I missing anything? So path is created. Okay, so if this is not the case, that is if it's not reachable actually. So what we would do, is there anything told in the question? Yeah, so if it is not reachable, we have to just return a list with only start, right? Okay, fine. So else my S path dot append would be the start vertex. Anything else? Return the list or return. So you have to return. You have to return it. The path that we created, return the. Now see, one thing is there. We have to return it in which order? Sample. So source start is 8, right? End is 7. So my end is at the last of the list. Okay. And here we are actually appending the start. So start is at the last of my list, is path list. Okay, anyway, so we can just print it from the other end. That also works. So I hope it should work. Yeah, fine. Yeah, so since I wrote the code in this manner, that I am appending each node, right, one by one. So my last node in the append path is start node, right, until and unless I'm getting the start node. Okay, but the question actually is asking you to print the list in the manner that the start is the first node and end is the last node. That's actually logical. So end is the last node. So I just printed the list in the reverse order. That's it. Fine. Yeah, so this was a little bit more involved code. This part is simple BFS, the classical BFS thing. Okay, the only thing that we did is this part got a little bit confusing, but it's very simple thing. If you do it on your own, you would understand. Since I kind of did it and explained it, became a little bit confusing. But basically, this is you are simply using the path dictionary in order to find the path, find the nodes in between the end and the start vertices. That's it. Fine. In order to do that, we just use this while loop until and unless you see the last node as the start. You just continue the who is the parent, the parent of parent, parent of parent of parent, that thing, and that is done using this line. Fine. Okay, so it's 8:40. Any doubt? Those of you are here.
No, sir. Fine. The return function is essentially to take the last node, right? To return.
Yeah, I'm just returning the path that we created. Only thing I coded it up in a different manner, so I just printed it in the other way. Since it was asking the start vertex to be
the opposite way.
Yeah. If you just coded it in the other way, start from the end. I started from the level end, right? You can start from level start and go up to the end and give the condition S path of -1 not equal to end, and right over here start equal to path start, and proceed accordingly. Append start, append, just the reverse thing. Then you can just directly print the list that you created. Fine. Yeah. Okay, fine. Thank you all. So there are other questions also for the live coding. We could not address all of them. On Saturday or Sunday, one of the days, we would discuss some fundamental coding topics of this week's 4, and then we would discuss the live codings. Fine. Yeah, sure. Thanks for attending.
Thank you, sir.
Yeah, thanks.
Thank you, sir.
Thank you, sir.